Hey everyone, welcome to The Explainer. Today, we're jumping into a really fascinating journey tailored specifically for you B.Tech students out there. We're going to bridge that gap between the theoretical physics you've been grinding through in your textbooks and the applied, tangible engineering that literally shapes the physical world around us. I mean, if you've ever spent hours, and I know you have, calculating forces in engineering mechanics, or staring at stress-strain curves in strength of materials, and you found yourself wondering, okay, but how does this actually help me build something real? Well, you are in the perfect place. Today, we're looking at the ultimate synthesis of all those subjects, machine design. Okay, let's dive into this. How exactly does a raw, abstract idea floating around in your head actually become a reliable working machine sitting on a factory floor? I'll tell you one thing, it definitely doesn't happen by accident, and you sure can't just guess the dimensions and hope for the best. It requires a highly structured, rigorous approach. We are going to unpack that exact blueprint today, taking you all the way from the initial spark of recognizing a problem, right to the point where you ensure the final product doesn't just, dramatically fail under pressure.
So here's our roadmap for the Explainer today. First, we'll define what machine design actually is. Second, we'll look at the classifications of design. Third, we'll walk through the general design procedure. Fourth, we'll define the factor of safety. And finally, we'll wrap up with designing for ductile versus brittle materials.
All right, part one. What exactly is machine design? Let's start by looking at the big picture here. Fundamentally, machine design is all about formulating a plan to satisfy a specific need. We are out to create new machines or improve existing ones. But, and here is the critical takeaway for you as future engineers, it's not just about doing complex math or sketching a mechanism that technically moves on paper. It's really about creating something with a physical reality that is actually economical in both its production and its operation. You have to study existing ideas, conceive a completely new one, study its commercial viability, and then make sure you actually have the resources. I'm talking the money, the manpower, and the materials to turn that idea into a reality.
The source material gives us this absolutely fantastic quote, "Design is essentially a decision-making process." Think about designing something super simple like a chair. You have to make decisions right from the get-go. What's its purpose? Is it a comfy lounge chair or an ergonomic office chair? Who's going to use it, an adult or a kid? What material gives you the right blend of strength and cost? Let's say you choose titanium for a standard office chair. Well, you've definitely made a very strong chair, but a pretty terrible economic decision, right? A bad decision at literally any of these stages leads to a bad design and ultimately a bad product. If you decide on a specific engine capacity for a car, that one single decision ends up dictating the shape, the size, the whole shebang of the rest of the design features. As the designer, you are constantly weighing purpose, materials, and yes, even aesthetics.
Moving right along to part two, classifications of design. And this brilliantly illustrates what you're going to face out in the real world. As you step into your professional careers, you're going to encounter different levels of complexity. Basically, there are three main classifications you'll be working within: adaptive design sitting at the base, development design right in the middle, and new design at the very peak. And this hierarchy, it's based entirely on the level of technical skill, research, and pure creativity required from the engineer.
Let's break these down a bit. Adaptive design, well, that just requires ordinary technical training. You're basically taking an existing design and making some minor modifications for a new application, like, say, adapting a standard conveyor belt system to fit a new factory floor layout. Next up is development design. Now this needs considerable scientific training. You still start with an existing design, but you might throw in a new material or use a radically different manufacturing method. The final product might actually look completely different from the original, kind of like developing a brand new model of a passenger car. And finally, we have new design. This one is for the heavy hitters. Now, no new scientific invention is involved here, but it absolutely requires entirely new, highly creative thinking to solve a problem. Like designing a highly specialized transport vehicle to navigate an uncharted desert. It demands top-tier technical ability and a whole lot of significant research.
Okay, part 3, the general design procedure.
So, how do we actually go about executing a design? Well, we need a map. When you are tasked with designing a machine component, and sure, there's no single rigid rule for this, but this 8-step flowchart really represents the most logical, proven path. It takes you from a purely philosophical need all the way down to physical production in the workshop. So, let's walk down this path together.
Notice how incredibly logical the progression is here. Step 1 is recognition of need. You have to make a complete statement of the problem and figure out the machine's ultimate aim. Step 2, synthesis. This is where you select the possible mechanisms that will actually give you the motion you want. Step 3 is the analysis of forces.
Guys, this is absolutely crucial. You must find the forces acting on every single member of the machine and calculate the energy being transmitted. Because only after you know the forces can you move on to step 4, material selection. You have to pick the material that's best suited to actually withstand those specific forces.
Right, so once you have the forces and the materials dialed in, you hit step 5, design of elements. You determine the exact physical size of each member by making sure the calculated stresses do not exceed permissible limits. You have to guarantee nothing deflects or deforms in an unacceptable way. Then, step 6 is modification. You look back at your initial sizes and modify them based on past experience and manufacturing realities. Often, you're adjusting things here just to reduce the overall cost of production. Step 7 is creating the detailed engineering drawing with all the complete manufacturing specifications. And finally, step 8, production. That's where the physical component is finally born in the workshop.
Which brings us to part 4, defining factor of safety. Now this next concept might just be the absolute climax of this entire explainer. Listen, the real world is completely ruled by uncertainty. You can perfectly execute that 8-step flowchart on paper, and your math can be totally flawless. But when you physically go to build the machine, there are always going to be variations in the physical dimensions, there will be microscopic non-uniformities in the material's strength, there might even be an unexpected sudden impact load. Because of this massive, unavoidable uncertainty, we absolutely must design a buffer into our machines. It's the only way to prevent catastrophic failure. So the crucial point is how we actually calculate that buffer. We call it the factor of safety. Mathematically speaking, the factor of safety is defined as the ratio of the maximum stress a material can handle to the working stress, or design stress, you actually allow the machine to experience in everyday use. Basically, you intentionally assume a design stress value that is significantly less than the material's true breaking point. This ratio right here, that is your invisible shield against the unknown. And finally, part 5, designing for ductile versus brittle materials. Now, how we apply that factor of safety actually changes depending on the physical nature of the material we're working with. The sources point out a really critical distinction here. When you're designing with a ductile material like mild steel, for instance, it has a very clearly defined yield point. That's the exact point where it stops stretching elastically and begins to permanently deform. And because this point is so clear-cut, we base the factor of safety for ductile materials on the yield point stress. However, brittle materials like cast iron behave totally differently. They don't have a well-defined yield point at all, they just suddenly snap. Therefore, for brittle materials, we have to base the factor of safety on the ultimate stress, the absolute maximum stress before total fracture. If you use the wrong baseline here, well, the results can be pretty disastrous. So, what exact number do you actually choose for your factor of safety? Are we talking a factor of 2, a factor of 5? Look, it's definitely not a guess. The designer has to evaluate several key variables here. You have to consider the reliability of your material's properties, like will they degrade over time? You have to consider the reliability of the applied load. Could someone potentially overload the machine? You've got to evaluate the extent of localized stresses, how certain you are about the exact mode of failure, and how many simplifying mathematical assumptions you made back in step 3. The higher the uncertainty in literally any of these areas, the higher your factor of safety must be. Bumping up that factor ensures that even in the absolute worst-case scenario, the machine remains reliable and, most importantly, safe.
We have covered a tremendous amount of ground today, all the way from the core philosophy of decision-making down to the rigorous math of the factor of safety. But as you know, engineering isn't just theory. So I want to leave you with this final, somewhat provocative thought. The next time you're standing in your BTech workshop, physically holding a piece of mild steel or cast iron in your hands, ask yourself, how will the harsh realities of uncertainty, reliability, and safety impact the design you are about to build? Let that question guide your hands as you turn your blueprints into reality. Thanks so much for joining me on this explainer, and keep designing.